Hi, it's Mr. Anderson, and today I'm going to be talking about limiting reactants and percent yield. Sometimes we call limiting reagents, but those are essentially the same thing. And this is always going to occur in a chemical reaction. So before we talk about chemical reactions, let's actually talk about food. And so if we were making cookies, let's say we were making Nestle's chocolate chip cookies. This is a recipe for it. And if you were to go down your ingredients list before you start making the cookies and you see, yeah, I got the flour, I got the teaspoon of baking soda, I got 3/4 cup of sugar, but then you get down here and you look in the fridge and you realize, oh, I only have 1 egg and I need 2 eggs for this recipe. Well, chemical reactions work the same way. You've got reactants, and you can think of those as like the ingredients before the actual reaction. And if you don't have all of them, then there's going to be one thing that's going to limit that reaction. We call that the limiting reactant. In this case, it'd be eggs. Now, can I not make cookies anymore? No way. All you do is just cut all of these down. So if they only have 1 large egg instead of 2, then I just cut everything in half. So it's a 1/2 teaspoon of salt, a 1/2 cup of butter. And so it still works. I'm still able to make cookies, but I just cut everything in half. And so those coefficients that you see in front of equations, if you think of those as like the amount, is a good way to think about it. So let me kind of start by showing this in a visual sense. So if we're doing hydrogen combustion, and an example of this would be, this is in the main rocket chamber in the space shuttle. What we have in here is liquid hydrogen and liquid oxygen, and those are combining, and we're getting this huge exothermic reaction, which is creating a lot of the lift. So this would be the chemical reaction. Hydrogen plus oxygen yields H2O. If we actually draw that out, then here would be the reactants on the left side. This would be hydrogen gas and this would be oxygen gas. And then the products I haven't shown you yet. And so if you look at this, you know that H2 and O are going to combine together to make H2O. And so you should, if you pause the video right now, you'd be able to take a second and probably figure out what the limiting reactant is. Looks like we've got a little more hydrogen than oxygen. So what's the limiting reactant? Let's do the actual reaction. Whoa. So what do we get? We get 4 water molecules, and then we have 1 oxygen left over. And so what was the limiting reactant? The limiting reactant in this case was the hydrogen gas, because how many atoms of hydrogen gas did we have? We got 2, 4, 6, 8, and so we only had enough to make 4 water molecules. Now we had enough oxygen to make 2 more water molecules, but the hydrogen in this case were like the eggs in our recipe. They were limiting the reaction. Let's go to the next one. This is combustion of methane. Combustion of methane, what you're doing in that is you're actually combining natural gas, and that's methane is a hydrocarbon, so it's 1 carbon and 4 hydrogens, with oxygen just found in the room, and we're making carbon dioxide and water. That's how a Bunsen burner works. So if we show you the reactants that I happen to have in this really small area, I've got 1 methane molecule, and then we've got, looks like 4 oxygen molecules. And those are going to make water and carbon dioxide. So if you actually do the reaction, there we go, I get 2 water molecules, and I've got 1 carbon dioxide molecule. So what was the limiting reagent this time? Same thing. Again, we've got plenty of oxygen right here, but we've only got 1 methane molecule. And so what was limiting us was the methane. So we call that the limiting reactant or the limiting reagent. So what would be left over? Well, everything that didn't react. In other words, that oxygen that was left over is just going to stay as oxygen. It's not used. It's like the other 1/2 cup of butter that we used in our recipe. And so those are graphically kind of showing you what limiting reagents are. Unfortunately, atoms aren't this big in the laboratory. If they were this big, we could just look at how much we have and we'd be able to figure out which is going to be the limiting reactants. And so we have to use our friend the mole to actually figure out how much there is. And so let's say we've got this reaction down here. We've got methane plus oxygen yields carbon dioxide plus water. And let's say together I'm going to mix 2 things. I'm going to take 10 grams of oxygen and I'm going to mix that with 10 grams of methane. So the question that you could be posed with is, which of those is the limiting reagent? Which of these is the limiting reactant? Is it the methane or is it the oxygen? Well, you can't tell by looking at a mass, so you have to do some calculations, and we can't see the atoms, so we're kind of stuck. And so let me talk you through this process. First thing we do is we convert them to moles. We then compare the moles. In other words, we're going to compare the amount of methane and oxygen to one of the products on the other side. In this case, I've chosen carbon dioxide. We're next going to convert that back to grams, and then we're going to figure out all the possible products. And so if these steps are confusing to you, you may want to look at the video on converting grams to moles. So first thing we do is convert to moles. And so I'm going to put my grams on the bottom and then my moles on the top. These numbers right here are the formula mass, and so we're getting that from the periodic table. In other words, to get methane, we're taking the atomic mass of 1 carbon plus 4 hydrogens to get that. Okay, so if we look at it, what we've converted to, if I were to cancel out my grams of methane, is I've converted to moles of methane and moles of oxygen. If we do our next conversion, I can then compare the moles. And so on the bottom here, I have 1 mole of methane. I'm grabbing that from the top over here. And 1 mole of oxygen to 2 moles of oxygen. Now where am I getting 2 on the bottom and 1 mole on the top? I'm doing that from my actual equation here. And so there's an implied 1 in front of the methane right here. And so that's why there's 1 mole here and there's 2 moles of oxygen. Why did I only put 1 mole of carbon dioxide on the top? Because on the other side, on my product side, there's only 1 mole. Now we could have chosen, instead on this comparing moles, we could have put 1 mole of methane on the bottom and 2 moles of water. In other words, we could have compared both of these reactants with water, and we still would have figured out which is the limiting reactant. Next, I could convert it to grams, and I do that just by now taking the moles of carbon dioxide and figuring out the atomic or the formula mass of carbon dioxide, and then I finally get my possible results. And so if I had 10 grams of methane, that's enough methane to make 27.4 grams of carbon dioxide. So that's a lot. That 10 grams of oxygen, however, could only make 6.88 grams of carbon dioxide. And so what's the limiting reactant? Well, these equations or these conversions show me that I'm going to run out of oxygen long before I'm going to run out of methane. And so what's the limiting reactant? The limiting reactant is the amount of oxygen. In other words, 10 grams of oxygen only gets me 6.88 grams of carbon dioxide. And so that's the limiting reagent, the amount of carbon dioxide. And I can even predict how much grams of carbon dioxide I'm going to get. So if you think of yourself as a chemist, what you can now do is put in a 6.88 grams of carbon dioxide. You could work backwards and you could figure out exactly how much methane you have to add to get 6.88 grams carbon dioxide. And if you're a smart chemist, you're always, in any reaction that you do, you're always going to make your most expensive chemical as a reactant be your limiting reactant. So you're not going to use any bit more of that. Okay, the other thing I mentioned I would talk about is the percent yield. And so in this theoretical experiment, we're going to get 6.88 grams of carbon dioxide. That's with all the oxygen reacting with all of the methane, but that never happens. So this is what we call 6.88 would be a predicted yield. If everything went perfect, in other words, if every molecule of methane reacted with every molecule of oxygen, we'd get 6.88 grams of carbon dioxide. Now you can think about it, that's never going to happen. If you think about the billions and billions and billions of molecules, the chances that they're all going to react and some aren't going to be lost is really, really rare. And so lots of times your actual yield will be much less than your predicted yield. In other words, I might be hoping to get 6.88, but I only get 6.19. And so those two values can tell me the percent yield. And so the percent yield is essentially the actual yield, in other words, how much I get divided by the predicted yield, how much I was hoping to get. And so if I throw those values in here, you can see the smaller value is going to be on the top. That's how much I actually get back. And the percent yield is never 100%. And if I divide the top by the bottom and then multiply it by 100%, I get 90.0% yield. And that shows me that this is a pretty good reaction. In other words, I'm getting most of the product that I predicted I would be able to get. And so that's limiting reactants, that's percent yield, and I hope that's helpful.